Hello, I'm doing a presentation today on the Newton-Raphson root finding method. My name is Luis Romero. I'm doing this for my seminar class at Lamar University in the College of Mechanical Engineering. So the Newton-Raphson method is a method of finding roots for functions. So we have a function f of x. Let me change the color. We have a function f of x, and if we set it equal to 0, then the x that we would plug in to get that function to equal 0 is called our root. And sometimes finding the root of a function isn't very difficult, such as this example here. It's just x to the squared minus 1, so the root would be plus or minus 1. But sometimes you have more complicated functions like cosine x minus x squared, and that's not very easy. That's not a very easy root to find. Okay, so what does the Newton-Raphson method do for us, and how does it do it? So the Newton-Raphson method gives us a sequence of numbers that we hope converges to our root. Now, how do we get that sequence of numbers? Well, we use a Taylor series expansion, or I guess let me back up a little. So we need an initial guess, which is an x naught. So, and we'll discuss a little bit on maybe how to get that guess a little bit later. But the point is you start with a guess of where your function will cross the y equals 0 point. So we have a y-axis here, not very good y. We have a y-axis here, and we have an x-axis here. And where it crosses, where y equals 0, the x that corresponds to that is our root. So we want to have a guess maybe somewhere here and say, oh, we're guessing that this is our root. And, it's not actually our root, and it, doesn't have to be like very, very extremely close to it. I mean, there are conditions, but it doesn't have to be extremely close um, most of the time. So what do? We approximate our function at the point. So let me hold on. Let me make this a little bit clearer here. Okay, so we have something like that maybe. So we approximate our function at the point x naught as a, let me change the color, as a straight line. Not bad. So this would be the straight line created when we use a Taylor series about our point x naught. So this is the Taylor series here, and we put approximately because we cut it off at the first derivative. And I suppose you don't have to, but just to make matters simple, this is what we do, and this is the method. So you cut it off at the first derivative, and now you have our function approximated as a straight line. Now, say we plug in, or say we want to find where our technically new function is equal to 0. Well, we can solve for that. We simply just plug in, well, these are values already. This is f at your point, at your initial guess, or your function evaluated at your initial guess, plus f prime evaluated at your initial point, initial guess x naught, times x1 minus x naught. And notice now we have x1 because this is going to be our first real guess using the Newton-Raphson method. And just to make matters simple, we put it as x1. So solving for x1, we get that x1 is equal to negative, the negative of the function evaluated at x naught here, divided by the derivative of the function evaluated at x naught plus x naught. And that's simply solving this equation here. So now we can do this again. We can take our x1 and expand our function about x1 instead of x naught. Yeah, well, that's the next one. So we can expand our function about x1 and do the entire process over again. And instead, we'll replace our x1 with x2. And we can keep doing this, and we're going to get a similar equation for our x1, x2, x3. And in general, it'll be in this form. X of n plus 1 will equal to the negative of the function evaluated at xn divided by the derivative of the function evaluated at xn plus xn. And our hope is that this sequence of numbers, which will have x1, x2, x3, x4, x5 until we're satisfied with it, with our result. I mean, we don't have to go to infinity. At some point, it might be close enough for us, and in general, it will be. In general, we approximate the root within some tolerance. But we hope that this sequence, if we were to take it to infinity, would converge to our R, or our root. So this is a graphical view of what's going on. And we have in blue our function. We've basically graphed our function. And actually this function is f of x equal to cosine of x minus x squared, which we actually was our first example, one of our first examples on finding the roots in the problem slide. So this blue line, and let's see, let me change colors so we don't get confused here. I guess red. So this blue line is our function graphed out. And we did our process. We found x1. And actually our x naught was equal to 1. And our x1 is equal to negative f of 1 over f prime of 1 plus 1. If you recall our formula from before, basically f evaluated at x naught over f prime evaluated at x naught plus x naught. And with that result, which I don't remember off the top of my head because it had a lot of decimals, but with that result, we basically just plugged it back into our equation, our x1 back into our general equation where x of n plus 1 bear with me, x of n plus 1 is equal to and that's a prime. That's not noticeable. Okay, so we just plug in our x1 back into this equation. We get a x2 and so on. But our x1 gave us this point here. Notice that this line is the linear approximation of our function at our x0 point. So with our x0 point, we just found a x2 point. Sorry, with our x0 point, we found an x1 point. And using that x1 point, we were able to find another approximation, which is here. This is our second iteration of the new Raphson method. And notice, this graph, I don't know if you realized, is not one-to-one, meaning that 1 unit on the x-axis is not equal to 1 unit on the y-axis, and this was just done for to better view what's going on here. But notice that this x2, which would be here, is actually very close to our actual root. Yeah, notice this is a y equals 0 line. And, it's not, it looks close, and, it's not exactly close, but on the next slide we'll see. Sorry about the picture, it's a little bit blurry. But, so we have this, and this is actually 1-to-1. 1 unit on the x-axis is equal to 1 unit on the y-axis. And we have our first guess here, right? And with our first guess, sorry, our first guess was x0 equals 1, and with x0 equals 1, we got our first approximation using Newton-Raphson method, which was x1. Okay, and with our x1, we were able to get x2 here. And you notice now it's not exactly close, but it's quite close, considering this is only the second iteration. So this was just to get a better idea of what's going on here. So now I wanted to discuss rates of convergence, because not all root finding algorithms converge with the same rate. Some converge more quickly than others, and some more slowly. So here we have our general definition that is used to define quadratic convergence and other convergences, and we'll see a little bit what that means. So what's happening here is we have a sequence of numbers, which is what our Newton-Raphson method gives us. It gives us x1, x2, x3, x4, all the way to x infinity. You could go to infinity if you had the time. But it gives us a sequence of numbers, and we hope that that sequence of numbers converges to something. In our case, a root, but in general, sequence of numbers doesn't have to converge to a root. It can converge to something else, but our problem involves the root of a function. So we want our sequence of numbers to converge to that root. And what does this definition tell us? It tells us, or it defines quadratic convergence. Not exactly quite yet, but it defines convergence, and we'll talk about it. So we have a sequence of numbers. Say we have, for example, x of n plus 1 minus r is actually, it's not a very good color. not for this board at least. So we have our xy coordinate. Hold on. Okay. So we have an xy coordinate, which is y on the over here, and we have x over here. So, you know, and somewhere on this x-axis is our root, and somewhere we have our nth guess, or our nth approximation, not our guess. It's our nth approximation using Newton-Raphson, and you know we have x of n minus r is what we call our error, the difference between our approximation and our actual root. And you could do the same thing for the x of n plus 1, you know, that's somewhere maybe over here. And so that error would be this distance here. Oop. Be this distance here. Oop. Okay. So what is this definition telling us? It's telling us that we have our x of n plus 1 term minus our root, which is basically our x of n plus 1 error over our x of n error to the q power. And q is just a number greater than 0 and 1, 2, 3, 4. But for quadratic convergence, q is equal to 2. And rearranging this equation up here, and you know, the limit still goes to infinity. Limit of n goes to infinity. But this is just a way to kind of get an idea of what's going on here. It's basically saying our n plus 1 error. Let's go ahead and write this down here. Our x of n plus 1 error over here is proportional, you know, c is some number, is proportional to our x of n minus r error squared. So what is that kind of telling us? Say we have our x of n error turns out to be 10 to the negative 4. Well, if our n's, like if our approximation is sufficiently large in n, meaning say it's x of n, you know, plus, x of n where our n is maybe equal to 100, or, you know, it doesn't necessarily have to be that large. It can actually, this can actually happen much sooner. But say our x of n is 100, then not our x of n, our n associated with our x of n is 100, then the n plus 1 would be 101. And the error associated with so we have our x of n. The error associated with our 101st term, or n plus 1 term, it's very likely that that error will be, well, that's a 10, negative 4 squared, right? Which is what? 10 to the negative 8th. So that's a large reduction in our error with just one more iteration. And that's what it means to converge quadratically. It means that the error on your approximation is very likely to be the square of the previous error. And linear, it's not like that. Linear convergence, it's linear, and that's the word. Uh, it's not squared. It's proportional to the error. The error is proportional. The n+1 error is proportional to the n error. So as you can guess, that converges much more slowly. And this is actually a very quick way, one of the quicker ways that a sequence can converge. And I think this might have been a duplicated slide. Okay, so one of the things I want to talk about next is something called attracting fixed points, meaning the fixed points are attracting. Now, what does that mean? Well, when you have a function of some variable, and here we have g x of n, we call a number a fixed point of this function if, when you plug in that number into our function, you get that number out. So, and this is a little foreshadow because R is what we're going to use. This is kind of just to get you with the idea of what's going on here, that R is the root. And we'll see later why this is important. But but in general, R is just a number. And if you plug that number into our function, we get R back out. And so that's a fixed point. Now, a fixed point is called attracting if the derivative of that function evaluated at the fixed point, the absolute value of that, is less than 1. Now, why is this important? What is attracting? Well, when you plug in this an attracting fixed point into your function, you get, well, g of x, yeah. And then you plug in g of x into g of x, and you keep doing it, plugging in g of x into g of x, plugged into g of x. Eventually, that converges to something. And if these conditions are met, then what that converges to is R. So that's a few definitions that we're going to need for the next few slides. An attracting fixed point. Now, just to recap, a fixed point means that if you plug in that number into your function, you get your number back out. And attracting means that first, that it satisfies this condition. And what it actually means is that when you plug it into your function and then keep plugging in the output of your function back into your function, it'll converge to your attracting fixed point. So just a little recap. Now we want to talk about convergence. So I've put our fixed point discussion over here because it's going to be important. So how can we assume, I guess, that our Newton-Raphson method will converge, like the sequence we get out of that method will converge to our root? Well, we can try to prove it, and this will be not a formal proof, but it'll give you an idea of what's going on with the Newton-Raphson method, and maybe it'll give you a little bit more familiarity with it. And if you look at formal proofs, they'll make more sense. So written up here is our Newton-Raphson algorithm. Um, you have our x of n plus 1, plug in your x of n, and it'll give you a new x of n. Well, we can write this as a function, and we can call that g of xn. And, if you notice, I do like to foreshadow a bit on what's going to happen. So we call this a g of xn. And, this is the function. And I want you to notice something, that f of r is equal to 0. And so if we plug in r into our, oh, wow. If we plug in r into our function, then f of r is 0, meaning, and x of n is r. And that was supposed to be an arrow, but so we plug in our r for a function, meaning everywhere we see x of n, we plug in an r. And f of r was 0 because r is the root of our function. If you recall, our original problem was finding the root of f here. We wanted to find the root of this, and we assumed r was our root. Plugging that into f, well, we'll get 0. And that makes g of r equal to r. Now, if you recall our previous discussion, that makes it a fixed point of g of r. Now, we want to also look at the second derivative. Yes, essentially we're trying to prove these conditions over here. So we look at our, not our second derivative, sorry, our first derivative of g. And it's basically just a quotient rule and quotient rule for this term, and x of n is just 1, and the derivative of x of n with respect to x of n is just 1, and it equals this. And it's just a little bit of algebraic manipulation, but that's what it equals. And some things we've discussed previously, or some things that we need to happen actually here, and well, actually just here, I think. But as long as plugging in r into our first derivative function, as long as r does not equal 0, f prime of r does not equal 0, notice it's here, and yes, as long as f prime of r does not equal 0, and this second derivative is well behaved, like continuous, doesn't do anything crazy, then g prime of r, plugging in r, will equal 0. Now recall that f evaluated at r is equal to 0 because that's the root of f. Then we have that g prime of r is equal to 0. Taking the absolute value, absolute value of 0 is 0, that is definitely less than 1, then that's really all we need to say that. Not very good. There we go. It's really all we need to say that g of xn will converge to the fixed point. And one thing to note is that this is only proven for a root that has a multiplicity of 1, meaning in a factorization that it will only appear once in a factorization. Say you factor something. Let's see, what's a good color? Maybe red. It's kind of okay. Maybe you have something like this. Well, notice that this appears twice. X times x, meaning 0 multiplicity of 2. Negative 1 multiplicity of 1 only appears once. So this is only proven for multiplicity of 1, and there's a lot more that goes into multiplicity of 2 and so on. But this is just an introduction, kind of to get an idea of what's going on. So for now, just know that. Okay, so that was convergence, and now we want to prove quadratic convergence. Okay, so we have our g of xn, which recall is the function that gives us our sequence of numbers, our x of n plus 1. And we can expand that using a Taylor series expansion. And notice Taylor series expansion comes up quite a bit. It's quite important in many theorems, many mathematical proofs, and as well as a lot of other sciences, physics and such. So we expand, Taylor expand our x of n about our r. So doing that, we get g of r plus g prime of r times x of n minus r plus this term. And this term is just the remainder term as stated in the Taylor's theorem, which is just basically a explicit equation for the remainder of a Taylor series. And recall that g of r was equal to r, that g prime of r is equal to 0. That was a condition for convergence in general, that the absolute value of g prime of r was less than 1, and it ended up equaling 0, which was less than 1. And one more thing to note is that g of x of n is actually equal to x of n plus 1, the x of n plus 1 term. So plugging in, not plugging in anything, just simply rewriting things, you have that g of x of n, which was equal to x of n plus 1, g of r is just equal to r, g prime of r was equal to 0, and leaving everything else the same. Now just rearranging and taking the absolute value of, everything pretty much, and taking the limit as n goes to infinity, we get that x of n plus 1 minus r over x of n minus r absolute value squared is equal to g double prime of, I forget exactly what this term is. Well, I'm not quite sure. But now that we're on the topic, this is just a number here. Sorry. This is just a number between x of n and r. That's all it means. So meaning the entire thing is just a number. So what do we have? What are we saying here? We have that the error of x of n plus 1, recall, that's the error, over the error of the x of n term squared is equal to some number. call it C. Then this is telling us essentially that this converges quadratically. So in the previous slide, we had proved that it converged, and in this slide, we proved that it converged quadratically. So I did want to explore a few conditions, and there are several more, but these are just to get a taste of what some of the conditions are. And in general, for Newton-Raphson method, if you're using the method, a lot of times you'll come up with problems that you won't exactly know how do I say this? You'll come up with problems in your Newton-Raphson method. You're trying to approximate a root, and you're not getting an answer. You've done several iterations, but you're just not getting an answer. And if you aren't really familiar with the process, maybe you're just using something that was implemented into some program, then you might not know what to do. You just assume, well, I don't know what to do, I'm stuck. But looking at the proofs for several any method really, not just Newton-Raphson, but looking at the proofs can sometimes show you what conditions need to be met for something to converge or something to happen. So it really is good to be able to look at a proof and understand what needs to happen for that proof to be true. So you get to some step in the proof, and if that step, the assumptions in that step aren't true, aren't met, then the subsequent steps won't be true either. Meaning we prove something for convergence, and we prove that something converges, but if one of the steps, one of our assumptions isn't true for our specific case, then we haven't proved that our specific case will converge. If all the assumptions we assumed, we can show that they are met in our specific case, then we can safely use a method and be fairly certain that it will give us the answer we need. So one of the conditions here is that f prime of x is not equal to 0 for all x in some interval. Now I is an interval r minus b, r plus b, for some b that is greater than r minus x naught. So what does that actually mean? And why do we need it? Well, if you recall from our equation, it's a good color, x of n plus 1 is equal to negative f x of n over f prime x of n plus x of n. Now what happens if f prime of x naught, or f prime not x naught, f prime of xn goes to infinity? Well, this well, let's see. So if what is our condition here? F prime of x does not equal 0. So if f prime of x does not okay, well, f prime of x does not equal 0. What happens if f prime of x does equal 0? Then this term goes to infinity, assuming x of n is some constant. Some constant divided by 0, or a smaller and smaller number, is just going to get extremely large, meaning that our x of n plus 1 will go to infinity. Now, what does that mean in a graph? It's basically saying you started here. Right? This line will never touch the y-axis. Sorry, the y equals 0 axis here. It'll never hit any point here. So you're never going to get a guess. Okay. So that's one of the issues that can come up if you're starting initial guess or any number in this interval causes your f of prime of x to be 0 because you have some interval, you make a guess, your guess is some number on that interval, then there's a potential chance that one of your approximations will hit that number where f prime of x is equal to 0. So, maybe it won't happen, maybe it will, maybe it won't, but if it does, it's going to mess up the entire thing. You won't get another x of n. Say you get to the fourth iteration, x of fourth is equal to infinity, then x of 5, nothing's going to happen. You're just not going to get a good result. You're not going to get a result. And that's one of the problems that can happen in when you're doing this. What's another one? F double prime of x is continuous for all x in the interval. Oh, and let me just go ahead and go back to one real quick. I wanted to talk about, let's see. So you have, well, that's not very good for what I'm trying to do here. So let's go ahead and erase that. Let's erase this. Okay. So all I'm going to do is draw an x-axis. So your root is somewhere here. And r minus b, r plus b. So r minus b so you have some b, and so here r minus b and r plus b. Kind of gets away from you, but you have r plus b. Okay, and got b. So this is essentially your interval here, from here to here. Your interval, and your guess has to be less than b. When you subtract your root from your guess has to be within this interval, meaning x0 has to be somewhere in this interval. Okay. Now, let's see. So condition 2, that was just a little bit of more discussion on condition 1, and these aren't all the conditions. Let me just reiterate that these are just a few to kind of get an idea of what's going on. So condition 2, f double prime of x is continuous for all x in the interval. Now, this had to do with the proof for convergence. So let's see, if I recall correctly, you had that g prime of x was equal to, I think, f of x. And let's try to, and f double prime of x. And let's see if we can fix this. Yeah, that's okay. And over f prime of x And if I recall correctly, this is squared. Now, it's a little messy, but I think we can get the idea. So we have our f prime of x, f double prime of x here. If f double prime of x is something crazy, not continuous, then we can't quite say, we can't quite continue with the proof for the attracting fixed point. So we need this f double prime of x to be well behaved, to be continuous. If it's not, we can't be certain that our proof will hold. You know, if the assumption is true, if f double prime of x is continuous, then yes, our assumption, our proof will hold. That's if all the assumptions are met. You know, all the assumptions of a proof need to be met for that proof to be true. For any case, any specific case. So that's one of the reasons why we need f double prime of x to be continuous for all x in the interval, and that interval is the same interval here. So that was just a brief discussion, and I do encourage anybody watching this to try to seek out more formal proofs and you know, dig into what's going on here. You know, if this method is very widely used, not just for, you know, roots. I mean, yes, roots very important, but it's also used for optimization problems, meaning sometimes you can't find the derivative of a function, not the derivative of a function, but the optimizing point. And I suppose, yeah, the optimizing point of a function, which, what is that? What is the optimizing point of a function? F prime of x equal to 0. Sometimes you can't find this for whatever reason. You need to approximate it. Well, you can approximate it with Newton-Raphson method. It's useful for, I believe, computational fluid dynamics, and you know, I can't think of any more right now, but this is a very, very important method. Now, other methods are the bisection method, which we talked about earlier, but we won't be discussing here. It's just, it's slower. It's slower than this. It's not nearly, I think, as picky, because Newton-Raphson is kind of picky. There's a lot of conditions that need to be met. But a lot of times with Newton-Raphson, you just make a bunch of guesses and hopefully your solution will come out. And you know, there's a lot of ways to make sure that your solution is actually a good solution. You can graph it. Graphing it gives you a good idea of a starting point, and sometimes you can just go ahead and see how many roots your function will have, what starting point you need to use to get those roots for that function. So lastly, I wanted to point out some references I used in this presentation. Newton's method and fractals is basically what inspired the informal proof in the video. And an introduction to numerical analysis, second edition, has a very good proof. And again, all the proofs aren't the same. There's more than one way to prove something. I just thought the fixed point method worked well, was easily understandable. And thank you for listening to me, and